All right, let's start. So, hello everybody, and welcome to the Bureau of Economic Geology Summer Seminar Series. As you all know, this series is designed to showcase the hobbies and the interests of our faculty and staff. Today's speaker is Dr. Ken Wisian. Ken is the Associate Director of the Environmental Division here at the Bureau of Economic Geology, with a background in geophysics, and his main research is in geothermal systems. Just a quick reminder, please mute your microphone during the presentation out of respect to the speaker. If you have any questions, feel free to ask them in the chat, and we can take questions during the presentation and more at the end. So with all that said, I'll turn it over to you, Ken.
All right, let me share my screen. Okay, is that coming through okay?
Looks good.
Okay. Well, folks, hello, welcome back for another one of my offbeat topic talks. This is addressing geothermal power in the outer solar system. This is a little bit of an expansion and update on a talk I gave last month to the British Interplanetary Society. And I'm going to be publishing that later on, probably in their journal. Let me start with the problem. As we do more and more in outer space, particularly in the outer solar system, meaning from Mars on out, we face a problem of how to power facilities. We've worked it out for powering relatively low energy needs of probes, even mobile probes, but actual facilities, as we think about colonizing, which is a hot topic nowadays, or even just establishing robotic operations on the surface of some of these bodies, power becomes an issue. The solar panels that we're used to really suffer from the inverse square law as you go out. The power that the sun is giving you is falling off dramatically. And by the time you get to Jupiter, it's about 1/25th the energy density that is here. So yes, you can still do solar power, but you need very large arrays to get an equivalent amount of power out. The other methods that powered our deep space probe so far have been fission sources, fission batteries, working with a thermocouple on basically a radioactive pile. They have their own issues, particularly if you've got sensitive electronics or sensitive biology nearby of needing the radiation protection, but also disposal of sources if that's considered, and refueling. The radioactive RTGs, as they're called, wear out over time, over a couple of decades. And so you also face the problem of resupply if you're using those types of energy sources. A potential solution for on solar system body power is geothermal in the right circumstances. And that's what I'll go into in more detail here. Please also feel free to jump in with questions, type them in the chat either way, or you can wait till the end. I'll be happy to answer questions then also. Most of you have probably heard me talk about geothermal in some way or another before, so I'll keep this part pretty short. But the basics of geothermal energy are tapping a hot fluid body, at least terrestrially, a hot fluid deep in the Earth's crust, and using the differential of temperature between that high temperature reservoir and ambient surface conditions to generate power. Most of that on Earth, in fact, pretty much all of it right now, is generated in areas of tectonic activity, either where you've got magma bodies in the crust that are heating water up, or deep fractures and fault systems that allow water to circulate to great depths and get heated up, as you see in the Basin and Range province of the Western US. These formation fluids vary widely in their temperature. Hotter is better, but generally in the 150 to 250 C range for most of these systems. New advances in geothermal technology are opening up the door to geothermal anywhere, and that's what's really driving this reemergence of geothermal right now that we're looking into. The methods of extraction are varied. I won't go into them here, but involve either fractures or long coaxial flow systems or other types of radiator patterns in the ground. What we'll be looking at on these icy bodies is a little bit different, which I'll get into shortly. On Earth, the US is actually the leader in installed geothermal capacity, with getting close to 4 gigawatts of installed systems. But although we're the leader in absolute terms, in relative terms, we're not even close, with all that installed capacity representing less than 0.5% of the US energy grid. Other countries, particularly Iceland and countries around the Pacific Ring of Fire, generate up into the double digits of their electricity needs off geothermal right now. So my point being that terrestrial geothermal is a fairly well-established, if small, industry and scientific discipline, and is experiencing quite a resurgence right now. So what do we need to do to take this into the outer solar system? Fundamentally, what you need to do is shift the entire thermodynamic cycle about 200 degrees C to the colder side. That's the fundamental thing that needs to be done in the outer solar system. And also dealing with an ambient pressure at or near zero. Now let's work through some specific bodies, some of the outlier cases first, the most obvious of which is Mars, with both government and private ventures looking to send humans to Mars, and in some cases permanently or semi-permanently. You immediately face that energy issue. It's probably secondary only to how to survive in the radiation environment, but it's a significant issue. There has been a tiny amount of thought put into geothermal on Mars. But so far, frankly, I would say it's not particularly promising. It's not the best prospect, primarily because there's just little or no tectonic activity evident. There is evidence of fluid flow periodically of water on the surface of Mars, indicating that there's some temperature there and some reservoirs that might be potentially interesting, but clearly not widespread. It looks like, or it's estimated that the heat flow and thermal gradients on Mars are less than half the average here on Earth. So if a substantial subsurface reservoir could be found, it could be exploited. Although there's no evidence for the really high temperatures you'd want, you could still use it for direct use, heating, perhaps as the technology advances, electricity generation off a smaller temperature difference. But again, the lack of evidence of this being widespread means that if you're going to tap into geothermal on Mars, that's going to probably have to be your dominant factor that you look at on where to establish a settlement or a facility, as opposed to other factors that you may want to look at. So it would become an overriding factor, but again, kind of like geothermal on Earth right now is, the geology and geographics would dictate where you go or where you can generate geothermal, as opposed to the emerging idea of geothermal anywhere, both here on Earth and, as I'll show you, in the outer solar system. One of the other most significant outliers is Io, the most active tectonic body in the solar system. It's one of the moons of Jupiter, and as shown here, it's active, it's got a high sulfur content, and what you see here is essentially every one of these dark spots is an active volcano on Io. And that sheer intense level of activity could be the dominant showstopper in doing anything on the surface of Io. It's just so active, that there may not be a place that's feasibly safe, even for equipment, to survive for very long. If you could, yes, there is a lot of energy to tap, but not at the top of the priority list. So what does that leave? That leaves most of the rest of the smaller bodies in the outer solar system. So I'm excluding the gas and ice giants. But once you put those aside, many, if not all, of the rest of the bodies in the outer solar system have some potential or might have some potential. They're generally icy bodies. And as we learn more and more about them, it appears that some level of subsurface ocean is a very common feature of these icy bodies. And notice here, when you're talking ocean worlds in the solar system, you lump Earth in there too. Some of these have more or a substantial fraction of the equivalent of the amount of water on Earth. So there's a lot of water in some form or another to deal with in these settings. In a generalized nature, these icy bodies, and I'll frequently just say icy moons is nearly equivalent, putting aside Pluto, but they all have a somewhat similar structure basis to them. And that is an icy crust with an ocean below them of some sort, either a regional or hopefully more common, a planet-wide or body-wide ocean under the ice crust with some sort of central core. For my purposes here, whether it's rocky or not is not that important. It's a lot more important when you're searching for life. But the key aspects really are in this upper part. Some level of icy crust with some level of ocean body underneath. The thicknesses of these different units varies tremendously and is also very poorly constrained with our current knowledge. But the key factors from a geothermal point of view is that you have two things. You have a surface temperature that's around roughly minus 200 C, and that's a back of the envelope level figure. And a ocean dominantly of water, although that's variable too, at somewhere close to 0 degrees. And those are the key features, is that temperature gradient between the ocean and the surface. So here's a sampling of some of the bodies out there and their statistics, focusing mostly on some of the leading icy bodies out here. And what you'll see, the main thing I want you to look at here is this surface temperature. And it does vary widely for a variety of reasons, but let's round it down a little bit to an average figure of minus 200. Again, just for ease of calculation, for the back of the envelope level of detail that we'll go into in just a minute. You'll notice also that the crustal thicknesses vary widely here. And these are also, again, poorly constrained. There's obviously no direct measurement, but there's some very interesting indirect measurements that are used to figure out these starting points for the thicknesses. And then the ocean body itself, generally expected to consist of a brine of some level with with various salts and other minerals involved. The main factor there being that combined with pressure and impurities, you could change what the freezing point of the water is. But again, we'll round that and keep it to 0 for now. So with that background, let's dive into one of the best studied cases and leading cases of geothermal activity in the solar system. And that's Enceladus, which is a small moon of Jupiter, as you'll see here. It's only 500 kilometers across, although very round. It's right near that limit of how much self-gravity a body needs. And if you can see it here, it's pretty close in. It's a little spot here on the diagram, fairly close in, not that far outside the visible rings of Saturn. and close enough to where tides are a major factor for it. It's obviously very close to here, but it's also feels the effects of the other nearby moons. The largest moon of Titan is way off the picture to the right. The largest moon of Saturn, Titan, way off to the right here, is another interesting one in its own right, which I won't go into here today, but the only known body in the solar system that has a liquid cycle on its surface, in this case, liquid hydrocarbons that form lakes, have rain and snow and such on the surface. So you've got Enceladus that we'll look at here, a tiny, tiny little moon close into to Saturn. It had, what makes it most interesting is it has had some thermal mapping done on it. And you see those results here. What you see is that there are known plumes and geysers on Enceladus around the south polar region. And here it's been mapped out again with thermal imager. The sum total of the activity, which you'll also note occurs very distinctly along very visible fracture systems here. The total output, not well constrained, but around 10 gigawatts thermal, with individual geysers running around 100 megawatts thermal. That's a substantial amount of energy. Now, I'm not advocating tapping into active geyser systems. That's fraught with all kinds of hazards, but it's indicative of the level of energy that is currently flowing out on a pretty consistent basis from the south polar region here. Just out last week was an article starting to speculate, and I think a pretty good way, on these fractures here and how they're forming. And it comes back again to gravitational tides. These tides that are very strong on some of these icy bodies are, one, responsible for providing that sustained heat beyond just radioactive decay to keep substantial parts of these bodies liquid. But it is also responsible for a common feature you see in these icy moons, which is ice tectonic surface activity, as I'll call it. Combinations of fractures and other systems that are fairly analogous to some aspects of both terrestrial crustal dynamics and ice dynamics. And on Enceladus, what they've pictured in an analogy to Earth is tidal flexing causing the cracks to form in the ice crust here. And you can see a parallel, a direct parallel between, again, that south polar region we were looking at with these long fractures where there's actual geyser or plume activity, and the Ross ice shelf in Antarctica. So a very active area of research from a physics, planetary geology point of view, not so much from an applied engineering point of view yet. Another interesting target, but one I won't go into detail, but has some strong similarities, is Europa. What is most interesting about this is there is a mission coming up. The Europa Clipper will be one of the next major deep space probes to go, and will specifically study Europa. So it's shown here, this body, and again, an icy body with a lot of what appear to be fracture systems and other things in it. A lot larger, 3,100 kilometers in diameter, as opposed to 500 or so for Enceladus. And recent, or moderately recently, evidence from the Hubble of active plumes around it too. So you've got, again, plume activity that is not as solid, but looks pretty good to me. Evidence there, along with, if you look at these images, a somewhat similar ice dynamic, ice tectonic activity appears to be going on, and probably provides those breaks in the crust for the plumes to develop. So let's look at a back of the envelope level calculation of how much power you might be able to get out of a single geothermal well on one of these moons. And I'm using a basic power equation here. Again, it glosses over all kinds of inefficiencies and complications. But basically, you work with a temperature gradient. This is the reason I was going simple here, of 200 degrees C or K between the water body and the surface, an efficiency factor of 0.5, and that's probably grossly optimistic, a flow rate of a cubic meter per minute, which is reasonable for a terrestrial geothermal well, and far less than those geysers are producing. And looking at two fluids that are commonly used here in geothermal production, H2O, pure H2O, and isobutane, used in organic Rankine cycle engines. And what you come up with, if you plug these simple numbers in, are an output of around 7 or 8 megawatts of producible power. So consider that megawatts E per well. That's a reasonable, respectable figure of power. That could easily power a small industrial facility here on Earth, or in the US, that'd be equivalent to about 3,600 homes worth of power. So it's something worth looking into and really fleshing out a lot more. But, you know, that's an easy kind of a physics equation. What about the practical engineering that's involved? And there are some huge hurdles in this. I don't want to oversimplify it, but I would say they're probably less than the level of hurdles needed just to get sophisticated robots or humans to these destinations. So, you know, is it achievable? Yes. I don't see anything that's stoppable from a physics point of view. So what are some of the main engineering issues? Well, the first is reaching that ocean. If the average crustal thickness here is on the order of tens of kilometers, perhaps even hundreds, that's a lot to drill through. And we haven't gotten close to that level here on Earth. But there's a key feature which I think would give me hope, and that is the fact that you've got plumes and outgassing, which means at some point you're reaching an effective depth to these water bodies of 0. Or by analogy, maybe something like the spreading centers here on Earth, where you have the upwelling of magma, and for instance, you get Iceland's geothermal systems. So the point being that the crust is not going to be uniformly that thick. There may be other reasons that there are thinner spots, perhaps impact features, perhaps just the ice tectonics finds thinner areas, or there may even be the equivalent of terrestrial magma bodies in the crust. You have liquid water bodies inside the ice due to various reasons. So hopefully you don't have to drill through the average or maximum thickness of the crust to tap into these subsurface oceans. How would you do it? Well, you know, the idea of taking a full-size drilling rig into space, regardless of what Bruce Willis may want to do, is probably not that feasible, and would defeat a lot of the gains that you might get from geothermal power. I think the most promising aspect of this is melt drilling. That's something that has been proven here on Earth in the Antarctic and has been proposed for missions to the icy moons. Unfortunately, a melt drilling experiment did not survive the cut on the Europa Clipper. Duncan Young, who's listening to this, has a lot more knowledge of this area and what may be in the works. So hopefully he'll chime in at the end here on that aspect. But the basic idea being you heat up a probe and let it melt its way, perhaps with propulsion, perhaps using gravity to melt its way through the ice. As many of you are probably already thinking, well, so what do you do with the wellbore? You've got a couple of leading issues here. One, how would you case it? Again, the idea of taking kilometers worth of piping with you into deep space probably defeats the whole idea of doing geothermal. So what about being able to produce your casing on site through an advanced version of 3D printing, perhaps? You also have waste removal. You know, whatever your method of drilling is, you've got to remove the stuff you're taking out of the way. How do you do that? And then perhaps the biggest factor, at least from my geophysical point of view, is the borehole stability. All of these icy bodies appear to be at least moderately, if not extremely active tectonically. How can you know if your boreholes can be stable or not be sheared off once you're reliant on it or halfway through building it? There's obvious engineering work on materials. And although we've done a lot of work on basic metals and other materials used in space, we haven't done the work on the fluids that would be used in a power system. So there's work to be done there. Power plant design, an interesting topic. I don't see that there's anything revolutionary needed here, but there's interesting variations. On terrestrial applications nowadays, spent fluid is pretty much universally re-injected back into the ground for environmental reasons, to recharge the reservoir, to keep pressure up. But is that really going to be necessary in the outer solar system? You know, putting another well in to re-inject the fluids is probably, again, a killer on the economics of the project. So maybe you just vent it or dump it in some way, your spent fluids. With the level of geyser activity, I don't think you're likely to have a significant drain on the basic reservoir for an indefinite period of time. But you have the basic power plant design too. You know, is it a direct flash to the turbine? Is it a multi-stage closed loop system with heat exchangers that tap the waste heat off each subsequent stage till you run out of usable heat? And then again, what do you do with the very last stage of temperature? Maybe you use it for direct heating of your facilities. So there's many options on the power plant design. And then there's the construction, especially if you're, well, even if you're doing it with humans, but robotically, there's a lot to be done on remote construction there. But as we're seeing even here in Austin, 3D printing of structures, houses and small facilities is a reality here now, at our ambient conditions anyway. What about thermocouples? That's an area that I'm just starting to look back into now. And I'm hearing rumblings that there are some significant advances, but if you could do a thermocouple to where you could really skip a lot of the moving parts aspect of generating power off a thermal differential, that would be quite interesting. And then, you know, how will advances in superconductivity play into this? They could factor in multiple ways, including on the thermocouples. But as we advance the temperatures that superconductivity works at, that could also be an interesting factor into this whole area of research. So those, the drilling. Just to show you that I'm not making this up, these are actual proposals for melt drilling probes in the outer solar system. Again, unfortunately, there's no current plan that I'm aware of to employ one of these. Hopefully there will be in the future, but even if one were to be designing now, the typical lead time is a decade or more to get on site with a experiment. But again, I think very promising, and hopefully the experiments will continue in Antarctica on developing this technology further. So we've looked at the engineering aspects. What are the science priorities on this? A lot of what I've been throwing out there in the way of numbers and quantities and such is not terribly tightly constrained. So what should we be looking at? Well, the oceans are a clear priority. What are their dimensions? What are their chemical and physical properties? The probes that are coming to the outer solar system are, I think, being planned universally to try to fly through plumes and get some direct measurements of the chemical properties of these systems. So that could offer a whole lot. The way that it's fascinating geophysics involved in how the oceans have been inferred already, from a combination of morphological features of the crust, of the ice crust, to magnetic properties of these bodies, to the very subtle gravitational impact. So it's been a very interesting field to watch, at least from the sidelines, of how these things have been deduced. You also have the crust themselves, their thickness and properties. We can see the surface and we can infer a lot from the morphology, but there's a lot left to be worked out. And of course, on-site is always great to add to it. It would also be nice if you could drill some ways in to get some thermal measurements. They were going to try that with the latest Mars probe, but unfortunately the digging tool, which was going to insert a thermal probe, just didn't work well. And there are also proposals out there that involve craters as sources of plumes, as well as the ridges and fracture systems that we've looked at so far. Again, the tectonics, a lot of great modeling work done on this. Again, if we can supplement it with more detail and more measurements, more in situ measurements, that would be great. Surface heat flow maps, again, kind of first order data when you're looking for temperatures. Good work done on Enceladus. Obviously, we'd like to see a lot more in that regard, as well as detailed modeling of the entire systems. So that's an area I would hope to get into in the relatively near future. I'm in talks with some established planetary scientists to see if we can go after some NASA funding for this. I'll also say, I didn't mention this at the beginning, but I would like to see this personal, so this is not Bureau opinion, but I'd like to see us move somewhat in the direction of looking at the economics and resources of the solar system as a Bureau of Economic Geology. Why? Well, because we can. Two, Texas and New Mexico are the center of commercial space in the world right now, and probably will be in the future. And a large part, besides human settlement of advancing in the solar system, is going to be the resources, whether it's asteroid mining or getting materials off the moon or some such. We've got the expertise in multiple domains to look into this. And while there's been a lot of speculation, it's not as much on the economics and practical side of the resources as you might expect. So I'm hoping to nudge us further in this direction. So in conclusion, geothermal at least is worth looking into further in the outer solar system. Compared to the existing things we've got, short of fusion being solved, which is always 20 years out in the future, I think geothermal has some real potential in the outer solar system and is worthy of some more research and experiments. So I will wrap my talk up there, a little bit on the short side, but hopefully we'll get a lot of questions, and I can already see the chat. So please, let me stop sharing for a second actually first. And one question's come in: how would the initial drilling be powered? Well, that's a good question. My guess would be off of probably a radioactive source for initial until you could get this going. That's probably the highest energy density you can take out that way currently. Again, I think the size of array you'd need for solar is just probably not practical, but I'll leave that to the engineering side. So with that, let me open it up to general questions, and also specifically ask Duncan if he would like to add any amplification or correct any errors that I made in this talk as someone who's just started sticking their nose back into this area.
No, yeah, Ken, great talk. I'm technically not here. I'm actually on medical leave, but I wasn't going to miss this. Yeah, no, I think one of the aspects out there, which may be actually the biggest engineering issue, is the planetary protection side of things, since these are systems which are very interesting for life. And there's the regulatory aspects, which are starting to become important for some of the work in Antarctica, the stewardship buffers that they're having to put in place between the milk drilling exercises, other drilling exercises, and the bottom of the ice sheet. But right now, there really isn't a well-developed regulatory authority out there for managing, especially the commercial side of space exploration. So I think that's going to be an ongoing tension between efforts looking towards expansions of human into the solar system and the scientific motivations which are being used for a lot of that.
Okay. Yeah, that's a good point. And for those that don't know Duncan, he's based next door in the Institute for Geophysics, and Truth in Advertising. We're both fellow SMU PhD products. On that planetary protection, for those who may not be familiar, we kind of think of, when you say planetary protection, a lot of people think of like the Andromeda strain, protecting ourselves, quarantining astronauts so that we don't bring anything harmful back from space to us. But as we start to move outward to planets that, there's a decent expectation may or could have had life on them, like Mars, like these ocean bodies in the outer solar system, you have to flip that narrative over and go, well, how do we prevent, superficially contaminating our own instrumentation, but two, introducing our microbes or whatever into these other bodies. And so planetary protection is a very active discussion / debate in the academic world in this regard. And Duncan brought up, the commercial aspects. Yeah, that's, I strongly anticipate more of a Wild West environment in that regard, but technically, according to the very limited amount of international treaty on space that exists, the host country that a commercial operation is from is responsible for all their activities in space. And that includes, for instance, Elon Musk being a US citizen, we would be responsible for whatever he does on Mars. But beyond that, there really isn't much detail in that. Anything else you want to add to that, Duncan?
Well, I think two other things. I actually have to leave here shortly, but one on the, what was I thinking? So coming on Europa Clipper and its role in that. Europa Clipper it's a flyby mission. It's going to do about 40 flybys of Europa. And the two relevant instruments here are our radar, which run out of UTIG, which will be able to look at the attenuation, and from making assumptions about the composition, it's you can back out the heat thermal structure of the ice shell. But there's also a thermal scanning instrument very similar to what was on the Cassini that was used for Enceladus. So especially on night side flybys, it will be able to put, and in the polar regions where it starts getting cold enough, you'll be able to put some constraints on the geothermal heat flow that way. There's plans for a follow-up lander. It is not an approved mission at this point in time. They are going to have a drill. A paper came out in Nature Astronomy recently, in the last week, looking at impact gardening processes on the surface, and found that if you are going to be able to detect signs of life on Europa from doing surface sampling, you'd have to get at least 1 meter down to avoid the impact gardening process cycling things through the harsh radiation environment at the surface of Europa. So it looks like there will be a drill on any follow-up lander just to get past that problem. Meters probably not enough to maybe do geothermal flux, but certainly geothermal heat flux is a really important measurement for any such mission to make. And then the question I'd have is, one of the things that's been a big trouble for melt drilling in Antarctica is actually the surface porosity. And there's a lot of actually questions about the role of surface porosity in the evolution of the topography of Enceladus and also Europa, where you have this transition from an area where you're porous and you have to put down a casing and reliably seal off that casing without getting, fracking going on, and then transitioning into an area where you can use a more open borehole for the fluid flow. Do you have thoughts on the role of porosity on the engineering challenge here?
Okay, very interesting. Yes, it's not an area I dove into yet, but it definitely is interesting from a geologic point of view too. Thanks for the detail on the missions that are coming up. And I should point out, if I remember right, because I did see that article you mentioned, you were co-author on that Nature paper, correct?
I was not, but Becky.
Oh, I thought you were. Okay, I'm sorry.
Yeah.
Okay. still very cool that UTIG is involved in these missions and this research. Okay, 2 questions in the chat. If the well casing is 3D printed, what material would be used for the construction? Yes, good question. I think it depends on what you get access to in these settings. I don't think there's much in the way of usable materials most likely on the surface of these bodies. So my hunch would be you'd have to capture some type of asteroid and convert that into material that would be then printed out or made into your piping. So probably back to metals of some sort, maybe a ceramic, but that I'll leave that to the materials scientists to look into. Other questions or comments? If you got one, just unmute and go for it if you want.
I have one, if you can hear me well.
Yes, go ahead.
Yeah, I'm Cyril Grima. I work at UTIG and the Europa Clipper team as well with Duncan. And my question was, the idea for BEG to leverage his expertise in order to develop a segment into planetary resources, planetary energy, as you proposed, is actually pretty exciting. You know, is that a way BEG is considering right now?
Well, you're seeing as deep as it's gone right now, which is essentially me trying to combine a couple of my long-standing interests in space and in geothermal. So I just first presented this again to a conference late last month, so just a few weeks ago, and am starting to put out feelers to see if there's a level of interest from the funding agencies, which would be primarily ESA, NASA, or the commercial interests that are starting to reach out into space. But this is slightly, except in the Mars case, you're talking pretty long term here. On the Mars case, that's much more near term, but I didn't mention some of the unique difficulties if you're going to try to do geothermal power on Mars, and that is, instead of drilling through ice, you're drilling through rock, and you're not going to melt probe your way there. So now you're back to having a real problem, which may not be surmountable for a while, which is a substantial infrastructure of a drilling rig. So the bottom line is, I would love to see some applied research in this direction. I think there's a lot of good expertise around that would probably be excited about applying their knowledge, whether it's drilling, power engineering, fluids, materials, other things into this kind of setting. And am quite open to ideas and conversations with anyone who's interested. Got another question came in on chat. NASA does have this is from Duncan, this is informational. NASA does have a program called Cold Tech, looking at ice access technologies. Yeah, I didn't know the exact name of the program, but yes, NASA has funded some very good research on melt probes, and I don't know if it involves other technologies. And I'm now watching INSPIRS, I think it's called, for the right type of funding call from them that I could propose on with this. And again, reaching out to some friends in the planetary world to look for opportunities there. So this was done, this little bit of thought on this was just done pro bono in my spare time. More questions. We got a little bit of time if anyone has any other questions or ideas on this. All right, Duncan's got to go. Thanks, Duncan. I appreciate your input on this. And I'm not hearing or seeing any more questions, so I think that is a wrap for today. Thank you very much. If anything else popped in your head, you know how to reach me. Y'all have a good one.
Well, thank you, and let's all thank Ken for the great talk today. And please join us next week for another talk here at the Summer Seminar Series. And have a good afternoon, everybody.